The standard normal distribution, also known as the z-distribution, is a special case of the normal distribution, where the mean is 0 and the standard deviation is 1. Right? So anytime you have mean equals 0, standard deviation equals 1, that's a normal distribution. It's a special case. So we call this there's two ways to call it. So a lot of times we're just gonna call it z. So anytime you see a z in normal, that's what they're talking about. They want the mean to be 0 and they want the standard deviation to be 1. You also might see this. Remember, all that means is what distribution, that's my line, what distribution you're using. So that's normal, and then that tells you what the mean is, what the standard deviation is. And notice that there's a z. So again, the key thing here is if you see z, that's we call that the standard normal. And that means that mu is 0 and standard deviation is 1. As you can see by this picture right here, right? Mean 0 and then each standard deviation is 1. You might be wondering what the standard normal is good for. Well, it's good for a couple things. One thing it's good for is to compare two quantities that are under different means. So like, I'm like 5'11", about. My sister, she's about 5'8". Now I'm taller, but among men, or among their gender I should say, who's actually taller? Right, probably the average height for a guy is like probably around 5'8". Average height for a girl is probably around 5'4". If we knew the standard deviations, we could figure out who's actually taller in comparison to their gender. So that's one thing to do. Compare heights, compare grades in classes, other stuff. So if you want to compare two different things and they have they're under different means, we can use the standard normal to do that. And also, so we're going to use this a lot for, when you're missing something. If you're missing the mean or the standard deviation, we're going to use a z to find it. In both these cases, we have to use a formula. That's what we're going to talk about next. Now, here's a formula to transform our normal distribution to a standard normal, so the 0, 1, 1. And right here, as you can see, it's in the formula sheet. Just copy it straight from there. It's our only formula we have for normal distribution. Is this. Right? Everything on there you can kind of see we know. Z right there, that's the standard normal. That's the standard normal value. So that's the answer you're going to get, like 1.3 or 0.7. So that's the answer you're generally looking for. X is the value you have. So like I would put my 5'11" there, my sister's 5'8" there. Mu is mean. And sigma is standard deviation. Right, so it's actually a very simple formula. We have everything we need. Z is the answer generally looking for. Like, okay, I want to find the Z score. We call that. X is the answer you have. So your higher your score, whatever it is, and the mean is standard deviation, the stuff you have. That's kind of how you use it. Sometimes you're going to have the Z and you have to look for the X, but otherwise you just plug it in simple algebra. Other than that, Z scores work the same. A couple things to keep in mind though, since it is a Z score, if you ever see them ask you for like, use a Z distribution, right, Z normal, when you draw your little picture, that's the best I could do. This has to be 0, and then you have to go 1 standard deviation each way. The good thing about that is you know right off the bat, if you have a negative value, you're on the left side of the mean. You're lower than the mean. If you have a positive value, you're above the mean. That's why it's a standard normal. But again, other than that, it's kind of normal, right? If I say greater than z, that means the right-hand side. If I say less than z, you start on the left-hand side. If I give you in between, you can shade in between. So again, kind of thing to keep in mind, right? If I ever give you something is greater than, I don't know, 2, you're going to start on the right-hand side. If I say less than, if I say, oh, we have like 0.63 is less than x or something like that, you're going to start on the left-hand side. And we're going to do a lot more later in this video. As you can see right here, the book says the same thing I said, right? It's particularly useful when you want to compare two things. They're good for comparing things and finding missing mu and finding missing mean and standard deviation, which we're going to do in the next video, actually. So let's move on a little bit. Let's actually compare two things. All right, so look at Kelly scored 73 in history, where the class mean was 68. That's a great teacher. So there's her mean. That's Kelly's score. The standard deviation for that class is 10.2. Right, so my standard deviation is going to be 102. In mathematics, she scored 66. Well, I'm glad she's not in my class. So that's her score. That's been her x value sitting over here. That's her x value. The mean is 62. Whew. And the standard deviation is 0.06. Right, so that's gonna be 0.068. Let's see what class Kelly did better, air quotes, in. So the best way to do that is we're going to plug both of these into and see what the z-score we get is. So let's do history first. So in history, looking for the z-score, we have our x, she had 73, so let's put points. I'll put 0.73. I could have gotten a full number, but let's be rebels. Then minus the mean, so 0.68. Really would have just been easier if I just used full numbers, but whatever. I'm living. And then divided by the standard deviation, 0.102. Put that into my calculator. And I get 0.05 over 0.102, which works out to be about 0.490. Now again, you're like, oh, 49%? That's not 49%. That means the z-score is 0.49. That actually means she's above the mean. Right? Because remember, z-score has a general standard right here. That's a terrible curve. Where that's 1, 0, sorry. The mean is 0. Each standard deviation is 1. Remember, most of the population falls within one standard deviation, so like that's kind of the normies. The general population, and then out here is where it starts getting like a little better. So she kind of right there. She kind of falls in here somewhere. So 0.49 in history. So she's a little better than average. Not bad, especially for history. I'm not sure what that means because history is easy. But anyway, let's go math now, like a real class. Right. So in math, it's the same thing. She scored 66 minus her mean, which is 0.62. Over the standard deviation, 0.068. I put that into my calculator, and you're going to get 0.04 over 0.068, and that's going to work out to be 0.588 about. Again, what does that mean? That she's again above average. Yay for low expectations. But right here is 0, right? And she's a little further than she was over there. And again, she's still within one standard deviation. Not in the Fregoso territory or the Dr. Carter territory way down here. But 0.588. She's better in this case. Within both classes, she's actually better in math. That's a scary thought. That's a good math score, but whatever. So that's how you do the subject score. So again, about the same, but based on the class average and based on the class standard deviation, she's doing a little better in math than she is in history compared to everybody else. And that's kind of it for standard normal until the next video. So let's kind of move on to a little review, and then we're going to do little new stuff. So look at this one. 200 lifesavers completing a swimming race. The mean time was 10 minutes and 30 seconds, which is our mean. The standard deviation was 15 seconds. Estimate the number of competitors who took longer than 11 minutes, took less than 10 minutes and 15 seconds, completing the race between that and that, right? So this is kind of like what we did last class. So we have this. Our mean is 10 minutes 30 seconds. Now we can't work in minutes and seconds. We gotta convert it. So it's either we're gonna go seconds, which means multiply by 10 by 16, add 30, or we can move on to minutes. And actually I'm gonna do that. That's 10.5 minutes, so 10.5 minutes. So that's what this is gonna be, 10.5. Now with that in mind, my standard deviation, I have to do that within minutes. So that's 0.15%, 15 minutes out of 15 out of 60. Is 1/4 or 0.25 a minute, right? So it's kind of sucks. You gotta convert things, but whatever. Let's look at the first one. We're gonna do like one of these because once you get the idea across, you'd be done. But let's find probably I took longer than 11 minutes. Estimate the number of competitors who took longer than 11 minutes. So first we have to figure that out. So 10.5 is there. Here goes 11. Longer than means the right hand side. Longer than. Remember the way we're gonna put this into our calculator. Lower bound is 11. Upper bound is infinity, but we can't do that, so we have to put E99. In our calculator, we're going to put normal CDF. 11, E99. We'll put the mean, which is 10.5. And we'll put the standard deviation, which is 0.25 now. Put that into our calculator. So second distribution. Now remember, we only ever use normal CDF. We never use PDF. If I could cross it out, I would, but once I try to draw, it goes away. So let me recreate the Emperor's New Groove opening title. So second E, remember chemistry E. Then over here, 10.2, 7.5, I could read, and 0.25. There you go. Hit enter, and enter again, waste my life, and you get your score, 0.0227. Right, now this is the only reason I'm doing this as one example, and I'm only doing this part of it. That's a probability that you're going to spend longer than 11 minutes. They want me to estimate the number of competitors, right? So it's actually one extra step, which is, oh, there's 200 live competitors, so remember the way we do expected value? Right? It's n times p. That's my p. That's my n. Multiply them together. 200 times 0.0227. Put that into your calculator. So I'm just going to get my answer and times it by 200. And then voila. About 4.5 people. 4.55 competitors. Spend longer than 11 minutes. We call those the losers of the race. But that's it for that type of idea. So we're going to move on to a new idea right now. Before we move on, but keep this in mind, right? Out of 200 people, only 5 of them, or 4 of them, about took longer than limits. These people are slow, right? Like they're the back end of the people. That's what the results mean, right? If I was going to take this one, how many people took less than 10 minutes, 15 seconds? My guess is that very few people, and those are like the winners. Like those people who won the gold medal. They didn't get job applications to work at a different occupation. I don't want to be saved by them. Okay, so let's go to the second part. It's probably the most important part today. Quartiles or K values. So what this is, when we do normal distribution problems, there's actually 3 types of problems. The first one is, I like to say, the normal one, the standard form. When you go forward, where you find the probability. So what you did on the last video, right? Where I give you some x's like greater than 3, so you're going to go, you draw a 3, and you go greater than. Or maybe I say x is between 1 and 3, right? You could draw in between 1 and 3. Right? You want to find the probability? That's the idea, right? You want to find a probability. That's the easy one. Just put in your calculator, you put normal CDF, and you're good. That's the first type of problem we're going to do with normal. The second type of problem we're going to do with normal is we're going to go backwards. You're given the probability. You're given k equals like 0.3. Right? So now you have a percentage. Now it all kind of depends how I say. I could say that less than 0.3, so it means you start on the left-hand side. So this would be less than 0.3. Or I could say maybe the top half is greater than 0.3. So you start on the right-hand side. Right? But the second type of problem we're gonna do normal is I'm gonna give you the percentage, the probability, and for that one we had to do invert normal, and that's what the next half of this video is. So right, the first type of problems where I just find the probability you're greater than 5, normal CDF 5 to infinity. The second type of problem we're gonna start doing right now is I'm gonna give you a percentile or a quartile range. I'm gonna say, oh, find the number of people that are 95 percentile. That are less than 30%. That one you're going backwards. We're going to do invert normal. We'll show you how to do that. But right, so here's this problem right here shows you. Like, what if I give you this? What if I say less than k is 95%? We see it's a different problem than we normally do, right? Normally I give you k is greater than 3, and I want to find a percentage, or x is greater than 3. I want you to find the percentage. This is going backwards. I don't know what the k value is. I just know that less than k is 95% of what we're doing. So, right, in this one, they give you the percentage. You have the probability. So, we're going backwards. And that's the example I'm going to try to do next. Right here it just says use your calculator, blah, 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 blah. Okay, so let's do this example here. Now, a couple things, notice how to read it. That right there tells you it's a normal distribution. So I could draw my little normal graph. That's terrible, but whatever. Right? 23.6 is your mean. Remember, that's just a fancy way to say variance. Like this is variance because it's standard deviation squared. Variance is bigger. But really all we need is that, and that's standard deviation. Right? There's just a fancy way of giving a standard deviation. Then find k where x is less than k is equal to 0.95. Now I think I've mentioned this already, but in normal, unlike binomial, this and this are the same thing really. You're taking the sum, so it really doesn't matter if you include that one thing or not. So these are the same thing in normal. You learn about that more in calculus, but for us, those are the same thing. You learn why that is in calculus, but for now, just keep in mind, normal doesn't give a crap about that stuff. Binomial cares a lot about less than or less than equal to. Normal could care less. One last thing before we get started here is how to draw this. So anytime I say less than, or maybe I might say bottom half or something like that, smaller than, anything that means like lower. So something to this effect, x is less than k equals 0.3. You want to start on the left hand side, and that's going to be a key. So over here, start on the left hand side, that's a terrible graph. This is halfway, right? 0.5 halfway. Start on the left hand side. I can only go 0.3 out, so 30% out here, so something to this effect. Right? Starting from the left hand side, because it's less than k. Start on the left hand side, 0.3, blah, blah, blah. If I said x is less than equal to k equals 0.9, remember, I can also take off the less, it doesn't matter. Normal doesn't care. Draw your little thing. We start on the left hand side because it said less than. Here's halfway. So in 0.9, I gotta go past halfway. It's only 0.5. I gotta be over here somewhere. I gotta fill up all this stuff to 0.9. And that's the way it kind of works, right? Less than start on the left hand side. If it's less than 0.5, be on this side. If it's more than 0.5, you gotta start from here and then go 90% fill. Likewise, if I said greater than, or I might say top half, or whatever I say. In general, if you see something to this effect, x is greater than k equals, let's do 0.6. Right? That means you're starting on the right hand side. So if we draw a little thing out here, we're going to start over here, because it's a greater than. This is 0.5. Again, I got to go a little past it, so 0.6. Then I fill it all in. So that's how you draw it. There's actually another step we're going to need to get to, but that's the first step is how do you draw it. So left hand side, start on the left, greater than, start on the right. Less than, start on the left, greater than, start on the right. So let's go to this one. Find k for which x is less than k is equal to 0.95. So let's draw it. I got my little terrible normal diagram there. It's less than, so we're going to start on the left hand side. Here's 50%, this will show you. So I got to fill up 95%, so it's like over here somewhere, it doesn't really matter. That's our k. Fill this all up. Now, the way we do this, we have the probability. So the way we get rid of the probability is you want to do the inverse. So we're gonna do inverse normal in our calculator. Now we're only ever gonna use two distributions in our calculator for normal, and that's normal CDF and inverse normal. That's it. If I give you the values like x greater than 3, normal CDF. If I give you a probability, invert normal. So let's bring my calculator here. Right, I'm gonna go same thing we always do, second distribution. The third one down, remember we never use PDF, dumb PDF. For normal, that is. And normal CDF right here. And then here's the invert normal. So you hit enter, you get area, that's its probability. So like in this case that'd be 0.95. You get the mean, which in this case is 23.6. And you get the standard deviation, 31.6. So that's all it is. Area is your probability, right? Because this is technically an area underneath the curve. Again, that makes more sense in calculus. So 0.95. Mean is 23.6. Our standard deviation, that's just a fancy way of writing it, 33.1. Hit enter, paste, and you get 28.6 or 28.7 to keep it 36 fixed. So right, again, how you show work, you just show what you plugged in. Like, oh, I plugged in this. So we know what you plugged in. It's like, okay. And we got 23.6, 28.7. Man, I suck. I hate getting old. Lose my memory. So, you get that. Again, what does that mean? That, and look at it. keep in mind that should make sense. Halfway is 23.6. And they're saying that over here should be 28.7, right? 28.7 is 95 percentile compared to 23.6, which is 50 percentile. That's all it kind of means. So let's do another one that's a little tougher. So the one right here, Z is a standard normal distribution. So see that right there? So I love this problem. I didn't even know I picked it, but so good. Z is a standard normal distribution. You know what that means? Notice I didn't give you any mean or standard deviation. They expect you to know it. If they tell you this, you got to right away go, oh, mean is 0, standard deviation is 1, right? They expect you to know the vocab. Standard normal means that stuff right there. So they won't give you mean and standard deviation. They expect you to know it. But here's the thing I'm really going to focus on. They gave me Z is greater than K is 0.73. So let's draw that. Right? So like this. Notice it's greater than, so I start on the right hand side. 0.73, remember that's more than halfway. So here's the halfway mark. I gotta go more than that. So like over here somewhere. All of this is 0.73. And then my K here is my K. Now here's the one thing I haven't talked about. Invert normal only works when it's on less than. It only works in this case. That's it. I know it sucks. Think a calculator can program the other side, but it can't. So invert normal on the calculator only works this way. So if you have this, and you want to find the invert normal of this, I can't plug in 0.73. It's not going to work. Has to be, invert normal only works when it's less than or equal to K. Or less than K. Because again, invert normal doesn't count, doesn't care. So what I do is this. Remember I said all this equaled 1, right? Because it's like a probability. Max probability is 1. So if you want to find out what this side is, you just do 1 minus 0.73. And then this half would equal 0.27. So this corner right here, which is the exact same thing as saying 0.73 over there, is 0.27. And that's what I'm going to use for my area when I do invert normal in my calculator. So my calculator invert normal, I'll use 0.27, because again, it has to be the left-hand side. Has to be the left-hand side, invert normal. So it's one of those things. And then, since they said standard normal, I'm going to use 0 and 1. Then I'm going to get my answer. Let's plug it in and see it. Alright, so again, I go back to second distribution. Go to invert normal. Again, I had to use the left-hand side, so in this case, I gave me the right-hand side. So I had to do a little mathematics. And then go down, 0, 1, because again, they said standard normal, so you have to know that. It's the vocab. Hit enter. And negative 0.61 something. I'm not going to care because I'm going to embarrass myself again. So that's all you're going to be less than that in the standard normal. Again, standard normal, this means it's below the mean, right? In the standard normal, the mean is 0. And the standard deviation is 1. So it's just like over here somewhere. That's all that means. Let's try to go through these next few examples a little faster. So look at this one. Again, notice the normal, right? That's that giveaway. The normal they have to tell you, right? It's not like binomial where you kind of have to assume it, or like you have to kind of estimate it, guess it. Normally they tell you straight out, like, hey, this is normal. And there's your mean, right? That's a fancy way to write standard deviation, 5. 5, not 5 squared, just 5. 5 squared is a variance, right? And find a such that, again, notice right off the bat, they gave you the percentage probability. So I'm like, oh, I got to do invert normal on this. I like to draw it, right? No, it's less than side. So and it's less than 5, so it's only like the first half. And that's 0.378. So like that. Again, I like to draw it. IB loves when you draw it, so draw it. And right, if I want to find that, I'm set. It's on the left hand side. I'm good. I'm just gonna put invert normal. 0.378. They give me all the stuff I need. 23 and 5. I'll save the time of plugging it in. That's fine. Then we look at this side. They gave me greater than. More work. Right? If I draw it, remember greater than start on the right hand side. Halfway is around 0.5. I'm actually a little bit past it, so I'm like over here somewhere. All that is 0.592. And this is my A. Again, if I'm doing this one, I can't use the invert normal yet. Invert normal only works on this side. But luckily it's an easy fix. All you do is 1 minus that thing. And you're going to get 40.08. 0.408. Right, and that's what this side is. Right, so again, invert normal has to be left hand side. If you have the right hand side, just do 1 minus it. Easy fix. So now you have invert normal, 0.408, 23, and 5. And that's that example. Put that in your calculator. I'm not going to do it, but that's how you do it. Let's move on. Almost done. A university professor determines that no more than 80% of this year's history students should pass the final exam. That's harsh. I think 8% is a good percentage, though. The examination results were approximately normally distributed with a mean of 62 and a standard deviation of 13. Find the lowest score necessary to pass. Right? So we're going to use math to figure out how much we have to care in history. That sounds like my type of student. So exam results were approximately normally distributed with a mean of 62. That's the average. Standard deviation is 13. Right? We want the lowest score to pass. So right here, it's all about, again, interpreting what that means. No more than 80% of the students should pass. So what that means is, now it's kind of counterintuitive, right? He wants the bottom 20 not to pass. That's kind of what that means. So like, I know no more than means this. Like no more than means 80% is the max, but it's to pass. It's like kind of a double negative thing going on there. Not really, but he wants 80% of students to pass. So again, the way grades work, right? Top is good, not bottom. So from here, he wants 80%. Right? He wants this to be 80%, the top 80%. That's probably the best way to think about it, right? You're taking the class, he wants the top 80% to pass. So that's what I'm trying from the right hand side. So he wants the top 80% to pass. Right? Well, remember, invert normal doesn't work that way. I gotta use this one. So if top 80% pass, that means there's only 20%. He wants only 20% to fail. So let's find the value for that. Remember the way we do that, if you have the probability, you have to do invert normal. Now you have your area, 0.2. You have all the stuff you need, 62 and 13 for mean and standard deviation. Plug that in, and you get the value of about 51, I think 0.2-ish. So you need to score about 51 to pass the test. And if that scores less than 51, it's going to fail. And that's the idea with that one. Let's go to one final one. And it kind of combines both ideas. So let's look at this one. The volume of a cool drink in a box filled by a machine is normally with a mean of 530 milliliters and a standard deviation of 0.5 milliliters. 1% of the bottles are rejected because they're underfilled, and 2% are rejected because they're overfilled. Otherwise, they're kept for retail. What range of volumes is in the bottles that are kept? So they want to know what volume has to be to get kicked out on the lower end, and what volume has to be to get kicked out on the higher end. So we're basically going to find both sides, right? So look what we have, right? We have the mean. We got my standard deviation right there. Now they tell us 1% of the bottles are rejected because they're underfilled. So this is what I mean by what do you mean by underfilled, right? If X is less than K, some value, then that's considered underfilled. So that's going to equal 0.01, 1%, right? 1% to 0.01, not 0.1. So if I draw this, notice it's underfilled, so it's on the left-hand side. It's only 1%, so it's something really small like this. That's my 0.01, and here's my K. Right, and that's what I'm trying to find. I'm trying to find out what value is it underserved at. So remember, if you have the percentage, the probability, you do invert normal. Invert normal 0.01. They gave me all the information I need. Now remember, if they say standard, I use 0.1, but they didn't. You plug it into your calculator, and you get a value. And I got 501.836. So something around there. For the underfilled ones. So if you're anything below this, you're underfilled. Now the higher end on this side, right? So now they're saying overfilled. So that's greater than. So if you're greater than some value K, you're overfilled. That's 0.02. Right? Same idea. We draw it. Now I guess it's overfilled, greater than. I'm showing on the right hand side. So it's only like a small portion right there. That's 0.02. But as we've been doing all class today, all video, I don't know what to call it, all video, right? You can't, when you do invert normal, you can't do that. I have a percentage, I gotta do invert normal. I can't do the right hand side, it has to be left hand side. Lucky it's an easy fix. You just do 1 minus 0.02 and you get 0.98. So you get invert normal, 0.98. I have all information already. 503 and 0.5. Plug that into my calculator and I get 504.03 milliliters. So right, so that's the range you get. Your range is going to be, so let's actually answer the question what range of values the bottles are kept. My range is going to be from 501.8 to 504.03. Right, anything below that is underfilled, anything below that is overfilled. And that's the lesson.